Welcome to your lesson on linear regression. Here is a scatter plot. A scatter plot is a good way to represent data that is bivariate. If we were to describe the correlation here, we could say there's a strong positive linear correlation. Today we're going to take correlation a step further by creating what is called a line of best fit or regression line to best match the data. For example, for this data, if we were to notice this linear trend, we could approximate this line of best fit. It is the line that best fits all the data points, and this line can be used to then predict or be used as a function to find values along the data set. A line of best fit can be drawn by eye. However, this is not the best way, as it can lead to more than one line, like in this set of data. For example, we have this scatter plot, and here we can see three different lines, three different attempts at drawing a line of best fit. All of them can be justified in some way as a line of best fit, but the question remains, which one is the best one? So drawing by eye is not the best technique. In order to help us draw a line of best fit by eye, however, we can do what is called finding the mean point. So let's read the definition of line of best fit first. A line of best fit, sometimes called a trend line, is a straight line drawn through the center of a group of data points plotted on a scatter diagram. The line of best fit lies as close as possible to all the data points. So that's the goal, that the line you draw is as close as possible to all the data. Okay, to help us draw a good line of best fit, we can begin by finding a mean point. The mean point is one point on the line which will be found by taking the mean of the x values and the mean of the y values. So once you find the mean of this independent variable, you can plot that point using that mean and that mean. Once you have the mean point, you can draw a line of best fit, and it must pass through the mean point. So that mean point gives you kind of a reference point, and then it's easier to draw the line of best fit. Let's try that with this data here. Here we have data that has different fast food items, and it shows the total fat of those items and the total calories of those items. And we're going to see if there's a correlation and then find the line of best fit for this data. Okay, so let's begin by finding solving A and B, which is find the mean number of grams of fat and the mean number of calories. So to do that, you will enter these values into list 1 in your calculator and these values into list 2. And then you can run a one variable stat calculation for list 1 and then one variable stat calculation for list 2 as well. So you can find the mean here and the mean here. Please do that now. Okay, hopefully you found these values for the mean. For the mean of fat, it was 22.45, and the mean for calories was 457.27. Let's see, so now that gives us a mean point. We have a x and y value, and that mean point has been plotted right here. So you can see the mean point is just the mean of the x values and the mean of the y values. There's the mean point. So line of best fit has been drawn through that mean point, and then it's been approximated to be as close as possible to all the other points. So that's our scatter plot. Let's look at question D here, which says plot the mean point on your scatter plot. Oh, we got that. Okay, question E. Find the equation of the line of best fit. Okay, so now that you have this approximated line of best fit that passes through this mean point, how do you find the equation? Well, if you remember from our work in this unit, this semester, we can find the equation of a line by using 2 points. So let's say we use this point, our mean point, and this point here, because that line seems to pass through 0, 200. So use these 2 points, first find the slope, and then use the equation y minus y1 equals m times x minus x1 to create a linear equation. Try that now. Okay, hopefully when you calculate the slope, you use the slope formula, and you took that y value minus this y value over the x value minus the x value, and you got a slope of about 11.5. Then using this form of a linear equation, we can create a linear model that for this line of best fit. That simplified is this. Notice this is 199.1, that is our y-intercept, and again we used we notice that the y-intercept is close to here, so 200, 199, very close. So that looks like a good equation for this line of best fit here. Okay, so once you have a line of best fit, again, approximating one, you can find a mean point and then find a line through that. Once you have a line of best fit, it's important to consider something called interpolation and extrapolation. So there are two types of predictions you can make. So once you have a line of best fit, you can use it to predict data. Interpolation is when you make predictions inside the domain for which your data points lies. So notice here we have in here it says interpolation. So here's the first data point, here's the last one. Interpolation is when you use your line equation to estimate values within the data set. Extrapolation is when you make predictions outside of the domain. So here notice we're beyond the first point and here we're beyond the last point. So this is extrapolation. The accuracy of interpolation depends on how strong the linear correlation is. So if these points, this one looks kind of like a moderate correlation, but if these points were really close together and it was a strong correlation, then this line would be a very good representation of all those points. And therefore, using the line to estimate values along the line is a good estimation of the actual data. Extrapolation is often considered unreliable, as predicting becomes less accurate as we move further outside of the domain. So since we had no data out here, this line may not be an accurate description of what would happen if we did have data out here. So we can only really rely on our line within here to predict values. But when you go beyond our data, it becomes unreliable, because it is difficult to know whether the data will continue in the same trend outside the domain. Okay, so here's another kind of example of interpolation versus extrapolations. We have Aemon's height chart. So here is Aemon at the age of 0 at birth. He was about 50 centimeters in height, and then you can see over the years all the way to maybe up to year 17 we have a height just under 2 meters. So there's his height over the years. Okay, 3 questions you will answer. Number 1, can you use the scatter diagram to estimate Aemon's height at any time during his first 17 years? The answer to that is definitely. These points definitely have a strong linear correlation, so if we make a line of best fit, that line can then be used to find a height anywhere in there. Once you have an equation, you can just input an age into the equation and it'll give you a height, and that height will be very close to the actual height because this is very much linear. Question 2. What happens when you use the scatter diagram to estimate his height when he is 40 years old? Okay, I hope you noticed if you made a line of best fit, we can draw it here, and if you follow that line all the way out here until 40 years, that line, if you use the equation, will predict that his height is 3.5 meters. That's impossible. So this line of best fit, again, beyond the data here, we're extrapolating, and we got a very unreasonable value. And the reason for that is, of course, people don't grow very much after the age of 17 or 18. That's maybe when they've reached their maximum height. Question 3. Where can you use the scatter diagram to make an accurate estimation about Aemon's height? Okay, again, within the domain of the data set, which is from 0 to 17, this is interpolation, and that can be used to make an accurate estimate of his height. Anywhere beyond that, extrapolation, and again, it can lead to very unreasonable values because these will not necessarily continue in a linear trend.